standalone. Most likely these two are mixed up, which means you go for one kind of assignment, and then you sequence them, you evaluate the quality of it. All right, and then you could vary certain things, the assignment or the sequence, and then you come to another plane, you evaluate them. So eventually you would able to find which one among those you have evaluated, you find which one is better. So in a way, it's like that. Okay, this problem actually is very much similar, as I mentioned, for this. How to solve that is very much similar to this problem, classic problem. Let me show you this. This is the definition of classic problem. It's called traveling salesman problem. And if you're taking a operation research module, then certainly this is a typical classic problem. The definition is quite simple. If you're given a list of cities and the distance between cities, if you look at this example, right? So we have A to F, 7 cities. Between, it looks like between every 2 cities there is not necessarily between any pair of cities. Between some cities there are routes. Between some cities there's no route. For example, between A to G there's no direct route. Okay, but anyway, so all the available routes are listed with the distance between them. That we actually consider this distance as some kind of cost, because the distance will be related to the petrol you use or whatever, or the transport cost. Okay, so the question is, okay, now we want a solution. We want to make sure that the traveling salesman visits every city only once, and the overall distance traveled should be minimized. So that is quite understandable. We are, in our daily life, we are facing this kind of decision making all the time. Even in Singapore, if you go on the weekend, you go to somewhere, and either you drive or ride a bike, or you take public transport. You roughly know either you want the quickest way to go, or either you want the most economic way to go. All right. So every day actually we are facing these issues. So this kind of problem, classic problem, the issue is for a small size problem, you could try every possible solution and do the evaluation, and then you find, which meaning that you can conduct exclusive search. But anything I think beyond like 15 or even 20 cities, you could face a huge problem. It becomes, the solution space becomes that huge. There's no way, even you use your computer, you can't do that. There are, even nowadays, there are still people try to find better solutions. So what you have is, there are those so-called internationally recognized benchmark problem, like 50 cities or 70 cities. And if you have an solution algorithm, you can go there to test your algorithm against those existing solutions. All right, and there's no way actually you deceive people, because so far for the 50 or 70 city problem, there's no best solution yet. Or there is a so-called the best so far. Okay, we don't know the best yet. So if your algorithm can find a solution better than that, and then yours is better. But anyway, so this is actually a typical optimization problem. So many solutions. If you come back to our problem, okay, let me show you. If you look at our problem, it's probably even more complex than the TSP. It's definitely more. For example, in this simple example, I have 6 machine features already recognized, right? Okay, I link these because there is a cost itself. There is a cost to machining, so-called to machine a certain feature, And in between there will be plus you need to add the cost of so-called setup changes in a way, costs there as well. So eventually you could have a link possibly from one phase to the other. Most likely the links are ordered. Rather than those available routes between different cities. This one you have more actually so-called available routes. That's the first thing, the challenge. The second thing is not necessarily, for example, eventually you would decide a certain so-called sequence, right? Visiting sequence. For example, let's see, you do this. Okay, I simply show a single so-called like a route to visit those features. But there is a problem here. In the TSP problem, there's no such issue. But here we do have, we call it the precedence relationship, which means this kind of a constraint, which means, I'll show you one example. The sequence, in some cases, the sequence of machining two features may not be, reversible. I'll show you this example. For example, normally here at the top, I use a pen. On the top there is a step, overall there's a big step, right? And then there is a group of these two or three features here. In this case, physically, you can't possibly remove the bottom intersecting feature without machining the top one first, right? You have to remove that piece of material first. So in machining, there is always this kind of constraints. You have to identify this kind of constraint first. And you apply it. You can apply it here, okay. So which means between two features, there's only one way. You can't do the other way. Okay. So this is another set of extra constraints to make the problem even more complex than the TSP. Okay. So eventually, you can borrow some kind of a solution algorithm from TSP because people are studying traveling salesman problem for many, many years. There are many different kinds of solutions. You can borrow some of the solutions, but at the same time, you have to add this kind of a check in those solution algorithm. So in order to find a solution, and again, you could use two kinds of objectives. All right. The first, you could use cost. If there is no so-called requirement in terms of early delivery, you simply normally use the cost. But sometimes you could use the delivery as well. So these two actually very often, contradicting to each other. Because if you want to produce the part very, very quickly, most likely you would employ those very expensive machines. Okay, and go with that. So these are the issues we are facing, and so eventually we could use differences, more constraints regarding process selection and sequencing. We define this process selection and sequencing, or process assignment and sequencing. The difference between TSP and that is feasibility from one feature to the other. You need to check. Okay, you need to make sure that of course you can apply some kind of penalties. You could have that. You don't care. But what you do is if A to B is allowed, B to A is not allowed, so the cost from B to A, you could add a very huge penalty, to do that. There are many, as I mentioned, there are many available algorithms you could use. Those traditional heuristic, traditional optimization technique, and nowadays even people using generic algorithm and even use AI, machine learning approach to try to achieve that as well. Okay. And but still go on. I wouldn't, because of the time limit, I wouldn't go to the details. The last slides I want to show you that, okay, for generative process planning system with 3 building blocks, the two challenges, you need a lot of efforts. The first one is the feature recognition. Okay. You could borrow from somewhere, but you need to be very much aware where the problem is. Okay. Machine database, that one is actually you have to work on yourself. If you want to build something for your own company or factory, you have to, based on whatever available machines, processes you have. And number 3 is the solution algorithm for process assignments and sequencing. So these two simultaneous decision-making process, and you could use, borrow classic algorithms to solve. The current status is, what I can share with you is, for components or parts belonging to relatively simple categories, like rotational parts, like sheet metal parts, we do have generative process planning which can handle 100% of parts, because it's relatively simple. It's relatively simple. The features are relatively simple. Facial recognition and plus even machining process also relatively simple. Okay, but for complex parts, very complex parts, those belonging to aerospace or whatever, still we do not have a very so-called good such a system, okay, to handle, to achieve a level of 100%. Maybe I can foresee maybe even in the future, the problem is actually not only facing these systems. The reason we don't have a so-called perfect algorithm to handle complex parts is because as human process planner, even for us, we don't have a clear so-called logic to come up with the best solution. The reason is obvious. If you talk to any so-called expert level, this kind of process planner, very much experienced, always give you very good solutions. And if you ask them how they do the job, they don't have a very clear clue. They don't have step 1, 2, 3, 4 until 12, 10, 12, 13, 14. If we have, then we can put that into the system very easily. That's the reason. So the knowledge acquisition part from them is not, it cannot be done, smoothly or 100%. It's just like those doctors, especially practicing. I'm not talking about. I'm saying the traditional, like the medicine, and those doctors, they check, they check your condition, health condition with a touch of here. Your pulse, right, heartbeat, whatever, and they can tell, although not 100%, and that kind of knowledge is quite difficult to acquire actually. Okay, so we do have those so-called traditional Chinese doctors with all different various levels, right? Some very high, some very low, and we try to develop a computerized system to simulate. Or to learn, their knowledge. And so far, very limited success. So in this area, actually, this is the challenge we're facing. Exactly in the same fashion or same manner. That's the issue. Okay, and well, that will be all. Okay, for today. Okay, I'll see you tomorrow morning. 8:30. Okay, 8:30. Yeah. So we